Hello everyone, my name is Yihong Zhang. I'm from Osaka University. I will present our paper titled Mutual Information-Based Preference Disentangling and Transferring for Non-Overlap Multi-Target Cross-Domain Recommendations. The main part of this work is done by the first author, Zhi. Unfortunately, he cannot come here today, so I will present this paper in his place. First, I would like to introduce the background of our research. In recent years, more and more online services develop recommendation systems to provide personalized recommendation for their users. These systems train the model to predict user preference and provide recommendation based on preference. To learn such a model, service provider collect interaction data between users and items. And an item can be the product in Amazon or video in YouTube. The interactions, for example, can be the click and purchase behavior in Amazon. Given a user item pair, the model learns embedding vectors to represent the user and item. The model name outputs a preference score to measure this user preference towards the item. After calculating preference scores between users and all items, the system recommends items with higher preference score to each user. Improving the performance of recommendation systems can increase commercial profits and elevate user experiences. In this work, we focus on studying multi-target cross-domain recommender systems. This type of recommendation systems transfer knowledge from multi-domains to facilitate the recommendations in all domains simultaneously. Generally, building a recommendation system requires a lot of user data to learn the model and to generate suitable recommendations. However, it is hard to learn a high-performance recommendation system with only sparse user data, such as the sparse purchase in the e-commerce platform. So as a solution, cross-domain recommender systems transfer knowledge from an external source domain to facilitate the recommendations in a sparse target domain. For doing this research, we identified two research problems based on the limitations we found in previous multi-target cross-domain recommendation systems. And then the limitation is mostly imposed by the requirement of using overlapping users and or items. The meaning of using overlapping users or items has two folds. First is to fuse and transfer knowledge in a diverse domain. Like you see in this example, even though we have 4 domains, if we can have the common users between among all the domains, we can then user preference and merge the interactions. But what if we don't have overlapping users? How do we fuse the knowledge without these overlapping users? This is the first research problem. And then the overlapping users is also used to learn domain share and domain specific preference. In multi-target cross-domain recommendation systems, there are shared preference and domain specific preference. In domain share preference, all the users from all domains are used to learn a global embedding which contains the domain shared preference. And then in domain specific preference, users from each domain is used to learn the local embedding which contains domain specific preference. But how about if we don't have the overlapping users, how do we learn the domain share and domain specific preference? That's our second research problem. To solve the above two research problems, we propose the framework for non-overlapping multi-target cross-domain recommendation. Our proposal is named as Mutual Information-Based Preference Disentangling and Transferring Framework, shortly as MITrans. MITrans consists of 3 modules, including semantic embedding, disentangle the preference learning, and preference fusion. Next, I will introduce the details of our solution for dealing with the 2 research problems. Our idea to solve the first research problem is that we construct a similarity-based graph to serve as the anchor for cross-domain learning. We use pre-trained language models such as BERT to convert item description tests into semantic embeddings and then cluster them cross-domain using embedding and similarity. As this figure shows, this graph is fully connected. In this graph, the nodes are source item clusters and target item cluster. The edges are weighted by similarity between the 2 clusters. With this graph, we can transfer knowledge among domains without sharing interaction data between the domains. There are 2 steps for transferring knowledge. First, we aggregate interaction into item embeddings with graph convolutional networks. Then we transfer domain space shared as preferences among the domains through the similarity-based graph. Because edges in this graph are weighted by the similarity between their nodes, the model can transfer knowledge by focusing on only clusters with similar semantic features. In this way, we can alleviate the impact from source noises to handle the varied preference across domains. Then move to the second problem. Our idea to solve the second research problem is that we propose a novel anchor-free DCE, or domain contrastic estimation, and CLUB, short for log ratio upper bound, uses to optimize the MI for mutual information for every pair of items. As this figure shows, we extract 2 types of item embeddings by using domain shared encoder and then domain specific encoder. And then we maximize the anchor-free DCE lower bound of mutual information to maximize the mutual information between domain share embedding, which can learn users' domain share preference. And we then minimize the anchor-free club of mutual information to minimize the mutual information between domain-specific embeddings. They can learn users' domain-specific preference. Finally, the preference fusion module can fuse knowledge in multiple domains to improve the recommendation performance in all domains simultaneously. Move to the experiment. To evaluate our proposal, we conducted experiments on the widely used Amazon dataset and the Douban dataset. We also evaluated 3 cross-domain scenarios, including 2 non-overlapping scenarios, the sparse and the dense, and 1 overlapping scenario. This table shows some information of our dataset. For each user, we use the last interaction as the test instance and the last second interaction as the validation. And measure the top K recommendation for all domains. For each user, we rank 100 candidate items, including 1 target item and 99 negative items, and randomly sampled from the negative items. And we recommend the top K items to the user. We compare our MI trends with the several baseline methods, including one single domain method and 4 non-overlap methods, two overlap cross-domain methods, and 2 overlap multi-target cross-domain methods. Only the CAR can learn both domain share and domain-specific preferences. The result, this figure shows the comparison result of recommendation performance for both Hira 5 and SIGIR 5. Higher values represent better performances. From this table, we can see that our proposed emergence outperform all non-overlap cross-domain recommendation methods and has no negative transfer issues in all cases. Emergence also achieves at least a comparable performance compared to the SOTA overlap cross-domain recommendation methods. It is worth to note that our emergence didn't use the information from domain shared users, so it has a much wider applicability. On the operation study, we found that semantic features is essential, but the domain shared preference in sparse scenarios sometimes hurts the performance. Result on the Doban dataset, we also found that emergence outperforms in most comparisons and has no negative transfer issue. We have the same observation in the operation study. Besides, we also conduct experiments to validate the impact of domain number. Our method is to validate all combination of 2, 3, or 4 domains. These figures report the average results over 2 domains, 3 domains, and 4 domain combinations. And from these figures, we can see that the increasing domains can improve recommendation performance, which demonstrates that emergence is effective in boosting recommendation with knowledge from multiple domains. In conclusion, we propose emergence for non-overlap multi-target cross-domain recommendation. It is effective in fusing and transferring domain share preference in diverse domains. It can also learn both domain share and domain-specific preference to improve recommendation. In the future, we plan to evaluate emergence in scenarios where data from different data sets can be used together, such as data set from Amazon, Douban, and Taobao. That's all for my presentation. Thank you so much for listening.